chose is the rice thresher, which its main purpose is to remove rice grains from their stalks as quickly and efficiently as possible with a motorized agitation system. The primary customers are rice farmers in developing nations, although this device can be used for other crops, and the secondary customers are wool producers, as this can be used as a cotton gin or a loom with some modification. We estimate the production volume to be around 60,000 a year. This is the exploded view of the original design. And here's the functional analysis, where we see a lot of the items and functions come from separating the grain. Here's our functional component mapping matrix. Again, most things happen and help move grain heads. This is our quad chart, our product family design, and here are the two module interfaces. The primary one being to remove rice heads, and the second one using a brush to comb wool. As I was saying, this is the original interface, and here's a second one where we have a bristled brush attached instead. This is the product family assembly diagram without modification, and here it is modified with the diversification happening during the rig stage.
Alright, it's time to examine our improved design. Appreciate this exploded view and see that the new design contains 10 unique parts, 18 total non-fastener parts in the assembly, including the set screw on the shaft and motor shaft connection, plus 2 bushings between the main frame and shaft. The new assembly has a total of 21 parts. This is 144 fewer parts than the original design, which totaled to 165 parts. All parts in this new assembly were redesigned to optimize manufacturing and assembly. The following section details our design for assembly tactics.
For design for assembly manual analysis, before we did the redesign, you can see that there's a lot of assembly time spent on the nails and boards, and we targeted this for redesign, as well as eliminating the fan belt and wheel. As you can see from the quad chart, those are not that functionally important, and we also saw an opportunity to consolidate the top frame and bottom frame, which we will discuss later. For that top and bottom frame consolidation, we did this to reduce part variety, because now we have 2 identical main frames. We also added features for easy insertion of the boards and designed it to have easy Z assembly. Doing analysis of our redesigned part, there is no impact on the function, as it continues to protect the user from the machine, and it also lowers our assembly cost as the efficiency increased to 0.48. For the module part, we decided to redesign the carousel, specifically the nails and boards, as that had taken up the most manual assembly time. We did this by reducing the part count and also reduced the fasteners, as the boards are now press fit into the rings instead of using fasteners to attach them. And we also added features of making the boards slightly curved to facilitate orientation when press fitting them into the rings. The analysis after our redesign included no impact on our function, as they still agitate the grains, but they do have a lower cost, which can be seen by the newer, bigger efficiency of 0.125.
For design for automated assembly, we selected the carousel subassembly. The function component mapping matrix shows that the highlighted subassembly parts all share functives, indicating potential for a redesign, including part consolidation. Additionally, they all either have high cost or functional importance, indicating an area for improvement. Here you can see the original carousel assembly with a high automated assembly cost of $2,546.63, largely due to the high part count induced by the nails specifically. Here you can see the effect of our redesign on the automated assembly of the carousel. The part count was reduced greatly by combining the boards and nails into one part, while also combining the spokes and rings. Combining the spokes and rings also promoted Z assembly within this subassembly, and utilizing press-fit boards into the wheels allowed us to reduce the use of fasteners in assembly. The new assembly cost reduced drastically to $123.43. With this redesign, there are no impacts to product function, but we expect changes in manufacturing costs with the wheels being machined and the new boards set to be injection molded.
Here we do process selection to find the best material and process for our new parts. We redesigned the spike plank, which agitates the grain based on the FCMM diagram. The new plank is one piece rather than two separate parts, which would need to be attached. Now we will see which best method is to create the part. Here we see that the standard. Here we set the standard tolerance to 0.5 millimeters for injection molding. We change the tolerance on the width and the height of the plank, as well as the radius, thickness, and height of the spikes to 0.1 millimeters to allow for press fit into the ring, as well as making sure that the spikes don't break and the thickness does not affect our process selection. Here's our dimension drawing. We can see all the critical dimensions and their related tolerances. Tolerances not stated have a tolerance of 0.5 millimeters. After selecting the material of ABS, we do process selection and find that machining and injection molding are the two viable options. Injection molding is our selected choice, both for time and for our larger batch size. Here, the second part we select that we redesigned is the ring. From the FCMM diagram, we can see that its purpose is to move the grain heads. Our new part reduces the number of parts we use. Here we see that we set the standard tolerance to 0.5 millimeters. We change the tolerance on the diameter of the axle hole, the length and width of the board holes to 0.1 millimeters to allow for press fit of the boards and the axle. The thickness can remain the standard tolerance due to it not affecting process selection. Here's our dimension drawing. We can see all the critical dimensions and the related tolerances. Tolerances not stated, again, have a tolerance of 0.5 millimeters. After selecting a material of aluminum alloy for the ring, we find through process selection that machining is our only option. Die casting would work if not for the tight tolerances we need to press fit the boards into and the axle into.
Alright, and now we have our design for manufacturing. First, we're going to look at the ring for a redesign, and when we put it through DfM Pro, we'll notice that some sharp internal corners could cause problems, as well as the fillets at the top are too hard to machine consistently, and we also realized we could make the stock thickness less. So, well, we did that. We used a standard stock instead of a custom one. For this design, we lessened the strictness of the radius so that it could be easier machined during the fillets, and additionally, we added 2 flat parts of the plate so that we could facilitate fixturing.
Here we can see that the overall impact on cost is about saves us about $49 total. This is in material cost due to it being thinner, and then in total setup cost, primarily due to having those flat sides for fixturing, as well as having more rounded edges.
Then, when we look at the spike plank through DfM Pro, we notice that we need a better draft angle to facilitate injection molding, and also that the current wall thickness is too much for very efficient cooling. So, what we did was we shelled out the bottom to make it hollow. We avoided the sharp corners for draft angles around the edges of it, and then we widened the thickness of the spikes to make sure that the rib thickness was proportional to the wall thickness.
This will save us about $28 in manufacturing cost, and this is due to that shelling out that Andrea mentioned earlier, so that saves us both in material cost and in machine operating cost because the maximum thickness is significantly thinner, and this, as well as the ring redesign, has minimal impact on function. And our total manufacturing cost of the entire rice thresher is about $725.